Getting to chapter 6, and now as we go through these, it's important to know that there is no set way to do things. I mean, I do teach a lot of dimensional analysis here, and the majority of the problems in this class you can use dimensional analysis to solve most of your problems. But the whole idea, though, is that you have to think through every problem. It's not something there's a general equation that's going to fit through everything. So you do have to think about the setup and when you go to the problem. And I do some of these problems, and I'm hoping that as you see the setups, you start to realize kind of the general pattern and how to analyze things and how to break them down. And I know in the previous chapters I went through a lot of that, but I mean now we're getting more and more where the scope is broader. So here's a problem here. A ring contains 1.1 times 10 to the 22nd silver atoms. How many moles of silver are in the ring? So this one's a little easy because it's directly with Avogadro's number. So we are given number of atoms and then wanted to convert to moles. So to do that, we just divide by Avogadro's number and check to see here that the units work out, and also that you get the answer in the proper number of sig figs, the 2 sig figs. So this one is a straight shot there. Here's another problem. Calculate the number of moles of sulfur in 57.8 grams of sulfur. So before we have atoms, now we have mass. And we have to then, we're not going to necessarily use Avogadro's number in this, we're going to have to use the periodic table. So looking at the periodic table and then getting that number there, the 32.06 grams of sulfur, that number is from the periodic table. And then going through dimensional analysis, you get the moles of sulfur that way. So that's how you solve that problem. So this one is similar. Instead of sulfur, we're doing aluminum, but we'll go ahead and do the same type of problem. We're given mass of aluminum, figure out the number of aluminum atoms, but I guess we're going a step further, not just mole, but atoms. So we have to convert to moles and then convert to atoms using Avogadro's number. So we're adding and building up and adding another step here. So this step there, and then this gives you the number of atoms. So it's building up in complexity with multiple steps. So now calculate the mass in grams of 1.7 moles of water. So you can see we keep on going, looking at this kind of problems, going backwards and further forwards, trying to figure out, new terms. And to me, it's a lot about the units. And of course, from this though, including that you have to figure out the molecular weight of water. So that's a new concept there. So 18 grams per mole, and you get these numbers here from the periodic table, the 2 times the mass of hydrogen and plus the mass of oxygen. You also get that from the H2, there's 2 hydrogens, so 1 oxygen. So you get the molecular mass of water there, and then put through the dimensional analysis to get the mass of water. So, and look at the number of moles in 1.8 grams of NO2. So again, looking at a new variable, and so was the number of moles NO2 in that. Okay, so it's a skill builder. I see. So we're not going to do this one. What is the mass of 4.78 times 10 to the 24th NO2 molecules? So from this, if you start to get the hang of it, you turn the molecules into moles, and then you multiply the molecular weight. That will get you the answer. So same thing from periodic table, get the molecular weight of NO2, and then put in the equations, go for the dimensional analysis. And when you're doing this, of course, in each step you're multiplying by 1, if you will, and then make sure the units cancel out and you get the right units at the end. And if you do that, you're probably doing it right. So determine the number of moles of oxygen and 1.7 moles of calcium carbonate. So now we look at each unit of calcium carbonate. We have to figure out the number of atoms. Each unit of calcium carbonate has 3 parts oxygen, and that's CaCO3, the 3 there, and there's no parentheses around it, so that we know there's 3 moles of oxygen to every mole of calcium carbonate. And so we'll do that, we just multiply by 3, and then we get 5.1 moles. So Carvone is the main component of spearmint oil, it has a pleasant aroma and mint flavor. So you added to calculate the mass of carbon in 55.4 grams of carvone. So we're given the mass of carvone, and now we have to figure out how much carbon is in this. So we're going to have to figure out the number of moles of carvone, and then the number of moles of carbon, and then multiply it by the molecular weight of, or I should say, the atomic mass of carbon to get the mass of carbon. So first things first. So get the molecular weight of carvone. It's 150 grams per mole. And with the 10, the C10, the subscript 10 tells you there's 10 moles of carbon per every mole of carvone. And then 12.01, that's just from the periodic table. So do the calculations, go through, and yeah, that's got a lot of carbon in it. But I mean, some things to think about here. We start off with a 50 grams, over 50 grams, and we should be, among other things, you should be getting less than 50. So if you get more than 50, you're wrong. And if you look at the atoms there, I mean, hydrogen's only 1 gram per mole, and oxygen is 16, and carbon is 12. So you'd expect most of it to be carbon. So this makes sense. So let's use some percentages as conversion factors. So we can consume less than 2.3 grams sodium per day. How many grams sodium consumed? So with a guy, how many grams of sodium chloride? So sodium chloride is 39% sodium by mass. You could figure this out if you want, but then you can then. I mean, that the 39% it's not necessarily have to be given. If you have the periodic table, you could figure that out. So let's use then the percent, and then the 2.3 grams, and then divided by the percent of that, and you can have 5.9 grams of sodium chloride. So does this make sense? I mean, among other things, if it's a smaller percent, you'd expect you should be able to, this number should be bigger, right? So think about that when you're doing your math. Is this number bigger? And this number is bigger, so it's good. So you've probably done it right. So calculate the mass percent of chlorine and Freon 114. So when we have these names, they're named. There's no convention for them. So I mean, I don't know what Freon 114 is. I mean, it has to be given to me. You can see it has nothing to do with the relative amounts of carbon, chlorine, and fluorine. So, but from this, if you look at this, chlorine's mass is 35.45, carbon's is 12, fluorine is 19. So you're going to expect it to be around 75%. I'm just jumping the math in my head. It's going to be around 75%. That's going to be in the high end there. It'll be around 70% chlorine. I'm sorry, not 70%. It'll be a little bit higher than 50%. So no, that's right. That's fine. That's 70%. No, that's right. So we'll see what happens. And to do the mass percent, the mass of chlorine over the total mass of the stuff, and I always think of like body fat percentage, right? So body fat percentage, the percent fat of your total amount of body weight kind of thing, and it's going to be lower than 100%. So let's do this, and it was pretty close. So just doing this here, you then the mass of chlorine is there, and then the total mass. So the total mass of chlorine there is 141.8 grams, and the entire molecule unit is 203.8 grams. So you divide the two, multiply by 100%, and you get close to 70%. And does this make sense? And like to me, yeah, it does, because I mean, well, I know what the I don't have the periodic table in front of me, but I'm a chemist, and I know this stuff. You shouldn't memorize a periodic table. That's a waste of your time. So I don't even have the entire periodic table memorized. I just have certain numbers memorized. And I've also worked with chlorine doing research, and I know it's a 1-to-3 ratio between the 35 and 37 isotope too. That's nothing, not really pertaining to this problem either. So it's just for me, I have the information on the tip of my tongue, but for you guys, but also doing the math and looking at the math and having a general idea of what the numbers mean is an important skill to have with this as you're moving forward. So how to obtain an empirical formula from experimental data? You decompose a compound in the laboratory, you get 24.5 grams of nitrogen and 70 grams of oxygen. What is the empirical formula? So what I really want you to think of is moles. Moles, moles, moles. When you see a mass of something, just go ahead and convert it to moles. And then from this, we're going to convert to moles, and we get 1.75 moles of nitrogen, 4.38 moles of oxygen. So now what do? We divide by the lowest number, and it's 1.75. So divide them both by 1.75, and then we get nitrogen to 2.5 oxygens. And so one thing about when you do chemistry and a lot of other things, botany is another one, and ecology. So you have to use discrete mathematics. I mean, whole numbers. You can't have a half an atom. You can't have a half a tree. You can't have your populations in biology have to be whole numbers. So keep that in mind. We use discrete mathematics in these fields, so we cannot stop here. We have to have whole atoms, and so when we look at these, we have to we have to multiply it by 2. So if it's the if it's 0.5, you have to multiply it by 2, and then we go through and we get the N2O5, so dinitrogen pentoxide. Or well, it's not. We don't actually know that, but that's the empirical formula. We know that the ratio between nitrogens and oxygen is 2 to 5. So with that, well, let's do this again, except now with percent compositions. And when you do a percent composition, it's similar to the previous problem, but just go ahead and use any convenient number. I like using 100. 100 is just easy. So say 100 grams and 60 grams of carbon, 4.48 grams of hydrogen, 3.53 grams of oxygen. And now then you convert to moles, and we have all these moles here. So now we divide by the lowest amount, and we get carbon 2.25 units of carbon, 2 hydrogens, 1 oxygen. So with the 0.25, that's a quarter. So you multiply that by 4. So same thing, when you get a 0.25, you multiply it by 4, and we get 9 carbons to 8 hydrogens to 4 oxygens. So that is how you figure out the empirical formula for that. So now we want to get empirical formula from reaction data. So here's another one, 3.24 grams of titanium reacts with oxygen to form 5.4 grams of the metal oxide. What is the empirical formula of the metal oxide? So we're not given the amount of oxygen, we assume it's just an excess. So to figure out the mass of oxygen, we have to take the 5.4 minus the 3.24 to get the mass of oxygen. So now we get the mass of oxygen there. And now taking each of the masses, so the 3.24 grams of titanium, the 2.16 grams of oxygen, we got to get the number of moles of oxygen. So here you can see we've gone through there, and then we divide by the lowest amount, and the titanium's lowest amount. Then we get the ratio of 1 mole titanium to 2 moles of oxygen. And I mean, doesn't it make sense? I mean, actually it does. I mean, one thing is you can look up that this is a mineral called rutile. It's a very commonly used used and found mineral. It's what they also put in some sunscreens. It's the titanium-based sunscreens that they put in there. And you can partially also look to the periodic table, see if the titanium is going to have a +4 charge, or perhaps. So that also limits your options there. So that's one thing that you can look at with this. So calculate the molecular formula from empirical formula and molecular mass. So we're given the empirical formula, and its molecular mass is 128.16 gram per mole. What's its molecular formula? So with this, the empirical formula is the smallest number of units. So we have to figure out how many units of the empirical formula is in this 128 grams per mole, and then multiply it by the proper number to get the molecular formula. So with this, and which is this is just what I've described. So the empirical formula molar mass is 64.09, and then we have to look at the molecular formula is 128. So if you take these two, you find out there's 2 units of the empirical formula. So we just have to take the empirical formula and multiply L by 2. And then we get C10H8. And I mean, this is reasonable. There are plenty of molecules like this. If you look for, like, as instance with carbon, there's C2H2. That's acetylene. That's the stuff they use in welding torches. And there's C6H6 benzene. And you can see they both, and benzene's a liquid. It's a very smelly aromatic liquid. They both have 1 carbon to 1 hydrogen, but they're 2 very different molecules. But of course, acetylene's going to have 2 units, and benzene's going to have 6 units. So, I mean, and this is reasonable. But if you were to do something like, if you take the material and use something like an activation analysis or something like that, and you can determine the percents of each atom from that, and then from that other data, like molecular weight, you can then figure out, what the stuff is in there. So I mean, this is something that people actually do in real life. So this is not just some crazy academic exercise that we're doing it to torture students. So hopefully you don't feel tortured, and you feel loved in this problem set, right? And unfortunately, this is the end of the love of the problem set, and I hope you have the rest of a wonderful day.